the last class we studied about refrigeration systems. So what are refrigeration systems? As we already know, refrigeration systems are devices which maintain an area or an object at a significantly lower temperature than that of its surroundings. One of the really important and not very often known part of refrigeration systems is something called humidity. Humidity is nothing but the presence or absence of uh, water or moisture in the air. Humidity is absolutely as important as the temperature itself. Too much or too little humidity can be disastrous for not just for health, but also in the case of processes where if you have too much humidity or too little humidity, it can actually damage whatever you're trying to build or whatever you're trying to maintain. It's also really important for in the case of preservation of not just of food, but also in the case of household items, where if you have too much humidity, it can always affect adversely whatever you have kept around, as well as too little humidity, things can dry out and get damaged. So the study of this humidity in the air is called psychrometrics. So today we are going to be studying about psychrometrics. So psychrometrics is nothing but the study of properties of air-water mixtures. To study psychrometrics, we will have to revisit certain things which we have already done in the past. For example, what are we actually studying? Psychrometry is the study of properties of air-water mixtures. Now, when we study the study of air-water mixtures, we assume air and water or the water vapor to be separate components. So we have got air and water. So what is air? Air in itself is a mixture of gases. We have got major components and minor or trace components. So the major components are nitrogen, oxygen, whereas the minor or the trace components are argon, carbon dioxide, helium, etc. Now, during this study of psychrometry, even though that normal air that we breathe and live in contains some amount of water vapor, we ignore this and we always consider air to be perfectly dry when talking about air and water. So we have got two components, air and water. Air is a mixture of gases which has major and minor or trace components, and it does not contain water vapor. This air is called dry air. Now, dry air consists of nitrogen, oxygen, 78.09% nitrogen, 20.95% oxygen, and trace gases such as argon, carbon monoxide, carbon dioxide, which amount to less than 1%. Now, water vapor, on the other hand, which is the second component of this air-water mixture, is naturally present in the air, and the amount which is present is dependent on the temperature as well as the availability of water in the area. Now, this is quite obvious. As the temperature increases, the capacity of the air to hold water vapor rises. So if you have to dry your clothes, one of the easiest thing you can do is to keep it in the sun where it's going to get heated up, and the water vapor is going to be absorbed readily into the atmosphere. But if you keep it in a cold area, it is not going to be absorbed as easily. So higher temperature, greater the capacity of the air. And obviously availability of water is also an issue. You will not find a lot of water vapor in a desert. Okay, so this is what we are studying: air and water mixtures, which is coming under topic psychrometrics. Other names of psychrometrics is also psychrometry as well as hygrometry. To completely understand the topic of psychrometry, we not only have to learn a few more topics or terms, we also have to revisit a few concepts which we have already studied. So one of the important concepts that we have covered in the past is certain laws of gases. one of the or one of the important laws which we have to consider is Dalton's law of partial pressure. Now, what is Dalton's law of partial pressure? It states that in a mixture of non-reacting gases, now this is very important, non-reacting gases, for example in air, nitrogen and oxygen do not normally react. So in a mixture of non-reacting gases, the total pressure exerted by the mixture is the sum of partial pressures of each of the component gases. So total pressure exerted by the mixture is the sum of partial pressures. Now, what do you imply by partial pressures? So to understand this, let's just take an example. We have a mixture of component gases 1, 2, 3, 4 and so on and so forth. The mixture is contained in a container at temperature T and it exerts pressure P. Now, partial pressure of component 1 is going to be defined when we have the same container and we introduce the same quantity of component 1. We take the same quantity of component 1 and introduce it in the container at the same temperature as the mixture. So we have got temperature constant and volume also constant. So when we have temperature constant, volume constant, the pressure which is exerted by the component 1 is termed as its partial pressure. Similarly for component 2, 3, 4 and so on and so forth. And the sum of these partial pressures, is equal to the total pressure exerted by the overall mixture. Now, in the case of air, pressure exerted by the mixture of water and air is equal to the sum of partial pressures of the water vapor as well as the dry air. Now, the mole fraction of the dry air, XA, can be defined as partial pressure of air divided by the total pressure. Partial pressure of the air divided by total pressure. Now, if we assume the total pressure as 1 atm and we substitute it here, we have XA, that is the mole fraction of dry air, is equal to the partial pressure of air. Similarly, mole fraction of water vapor, XW, is equal to partial pressure of water vapor divided by total pressure, is equal to, again if we substitute the overall pressure as 1 atm and we have mole fraction of water vapor is equal to its partial pressure. Another common term which we will come across is something called relative humidity, RH. It is denoted by the Greek letter phi. Now, we define relative humidity as the ratio of partial pressures of water vapor to the saturation pressure in a mixture at the same temperature. Now, ratio of partial pressures of water vapor to the saturation pressure in a mixture at the same temperature. What we are going to do is we are going to assume air as a container, all right, for representative purposes. So what we are doing is we are assuming air as a container. Now, air contains obviously air and some amount of water. Okay. Now, what is going to happen is that as the temperature increases, the capacity of the air to hold moisture also increases. As the temperature is increasing, the capacity of the air to hold moisture also increases. Okay. Now, if we have some amount of water in the air and we start cooling the air, at some point of time or during the cooling process, the amount of water present in the air is going to be the same as the maximum capacity of the air. Again, at some point in time, as you're cooling the air, the capacity of the air is going to be equal to the amount of water vapor present in the air. At this point of time, we say that the air is saturated. We say that the air is saturated. We define relative humidity as the ratio of partial pressures of water vapor to the saturation pressure in a mixture at the same temperature. So what we have is that the water in a mixture exerts some amount of partial pressure. And what would be the partial pressure when there would be the air would be in saturated condition? So that is the saturation pressure, and the actual partial pressure is PW. PS is the saturation pressure. Now, what we do is we assume ideal behavior of the gas. So we have PW is equal to MW RH2O T. Okay, we have got the partial pressure of water vapor into volume of container is equal to mass of water into gas constant of water into the temperature. Okay, where V is the volume and T is the temperature. Now we know that gas constant, that is universal gas constant, is equal to molar weight of the gas, any gas X, into its gas constant. Okay, mass of gas X is equal to number of moles of the gas into molar weight of the gas. Combining these two, we get this expression, that is mass of the water vapor into gas constant of the water vapor is equal to number of moles of water vapor into universal gas constant. Again, we do the same for saturated condition, where this is the saturation pressure into volume is equal to mass of water vapor at saturated condition, gas constant of water vapor into temperature is equal to number of moles of water at saturated condition into specific universal gas constant into temperature. Now phi, which is PW by PS, if you substitute these terms, we'll have MW by MS, that is mass of water vapor in the air to the mass of water vapor that would be required at this temperature for the air to become saturated, is equal to number of moles of water in the current mixture divided by number of moles in the mixture at that same temperature, which would result in the mixture being saturated, is equal to XW by XS, which is nothing but your mole fraction of water vapor divided by mole fraction of water vapor at saturated condition. Now, the relative humidity is bound by two values, which is 0 and 1. That is, your pressure of the water vapor or the mass of water vapor in a mixture can be 0, or it can be equal to the mass of water vapor at saturated condition. So it can be any value between 0 and 1. Between 0 and 1. Another term which we have to look at is something called specific humidity or humidity ratio. specific humidity, or also known as humidity ratio. It is denoted by the letter W. Now, this is defined as mass of water vapor M per unit mass of dry air G in a mixture. So what we know is that air contains, or air as we know it contains dry air plus water. Okay, so the mass of dry air is G. Here what we assume as mass of dry air is G, and mass of water vapor which is contained to make it the air that as we know it is called, or is denoted by M. And the ratio of mass of water vapor to the mass of dry air is termed as specific humidity or humidity ratio. Now, at any temperature, there is a maximum amount of water vapor that can be held in dry air. Okay, at any temperature, given temperature, there's a maximum amount of water vapor that can be held in dry air. Let's assume that that amount to be M max. So there's a maximum amount of this water vapor which can be held in at any temperature in dry air, and that amount of water vapor is termed as M max. So we get a limiting value of specific humidity or humidity ratio. W max is equal to M max divided by G. Now, in this state, when you have got the maximum amount of water vapor that can be held in the dry air at that temperature, the state is said to be saturated. That is, the air at this state is said to be saturated. Now what we are going to do is we are going to simplify this equation. W is equal to M by G into terms that we can readily measure or something that we can infer. So M and G are the mass of water vapor and dry air respectively. What we are going to do is we are going to substitute them with terms from the ideal gas equation. Now, ideal gas equation for water is that water vapor is partial pressure of water vapor into volume of container is equal to mass of the water vapor into gas constant of water vapor into the temperature. Similarly for air, partial pressure for air into volume of container is equal to mass of air into gas constant of air into temperature. So once we substitute for M and G, we have this equation. We have PW by PA is equal into RA by RW. Now we further substitute RA by RW as a function of universal gas constant and the molar weight of the respective component, that is air and water. Once we substitute those, we get this equation, that is 0.622 into PW by PA. PW by PA. Now we can also express PA as overall pressure minus partial pressure of water. So W, that is the specific humidity, is equal to 0.622 into PW divided by total pressure minus partial pressure of water. Now again, for saturated conditions, the partial pressure for water is equal to the saturation pressure for water. So we substitute that as Ws, that is the specific humidity at saturated conditions, is equal to 0.622 into Ps, that is the saturation pressure of water for that temperature, divided by the net pressure of the mixture minus Ps, that is the saturation pressure of water at that temperature. Another term that we have to cover is something called degree of saturation. Okay, degree of saturation. Now, this is defined as ratio of actual specific humidity and saturated specific humidity. Actual specific humidity and saturated specific humidity. This is just from one step earlier. So mu is equal to W by Ws. If we substitute the equation here, we get this. Once we simplify all of this, we get mu is equal to PW by PS into P minus PS divided by P minus PW. Now Pw minus Ps is also, as we know, is termed for relative humidity. That is the ratio of water, the partial pressure of water divided by saturated pressure, saturation pressure. So that mu is equal to phi into P minus Ps divided by P minus Pw. Now we have got two limiting conditions for dry air and for saturated air. Dry air and saturated air. Now in the case of dry air, we know that phi, that is the relative humidity, is 0. Pw, that is a partial pressure of water vapor, is going to be 0. That means that there's no water vapor in the air, so that it cannot exert any pressure. Its mole fraction is 0, and the weight and the specific humidity is also 0. So once we substitute that here, we get mu, that is a degree of saturation, also as 0. Next we have for saturated air. For saturated air, relative humidity is 1. This is a limiting condition. Partial pressure of water vapor is going to be the same as saturation pressure. So Pw is equal to Ps. And W, which is a specific humidity, is going to be that of the saturated condition. So thus, once you substitute it here, you get mu is equal to 1. To actually measure humidity, we require a certain number of parameters. Now, one of the important parameters is temperature. All right. However, temperature cannot be solely used, as you can have temperature, the same temperature for different mixtures of gases. So we have to come up with a reference system known as dry bulb temperature and wet bulb temperature. So dry bulb temperature is nothing but the temperature of air as measured by a thermometer freely exposed to it but shielded from external sources of radiation and moisture. This means that we take a normal thermometer and we measure the temperature of the air. Okay, so in this case it is around 36 degrees. Okay, now that brings us to the next term, the next type of temperature measurement, which is called wet bulb temperature. Now, what is wet bulb temperature? Basically what we do is that we take a normal thermometer and we dip its, or we surround its bulb with a wet cloth, okay, which is saturated with water. All right, it is saturated with water. Now as the water is evaporating, so let's just illustrate this. So we have a thermometer, and what we are going to do is that we are going to cover its end with a wet cloth. Let's just assume that this is a wet cloth and it is completely saturated with water. All right. Now, as this water gets evaporated, the temperature is going to reduce. The temperature is going to reduce. All right. As the water vapor is going to be evaporated, the temperature is going to be reduced. And the temperature as measured by this thermometer is termed as wet bulb temperature. It is termed as wet bulb temperature. Again, wet bulb temperature is temperature of air as measured by a thermometer whose bulb is enveloped by a cloth which is saturated with water. Now, why are we considering wet bulb temperature in addition to dry bulb temperature? As I've already mentioned that regardless of the type of mixture, you can attain the same dry bulb temperature. You take the same amount of mixture which has got different humidity, levels, and you can raise its temperature to the same dry bulb temperature. However, what is going to happen when you measure its wet bulb temperature is that the amount of water vapor that is going to evaporate at the same dry bulb temperature for different levels of humidity is going to be different. Thus, the amount of cooling which is going to happen on the bulb is going to be different. Again, we look at our example of the glass. Okay, now in each of the cases, if we had just measured the temperature, we would get certain temperatures. So it's T1, T2, T3, T4. Now we are measuring the mixture of the gas. We are measuring the temperature of the gas 1, 2, 3, 4 at different temperatures, and we are going to get different values of dry bulb temperatures. However, once we coat this once we coat this thermometer or envelop this thermometer with a wet cloth, which is represented by this aluminum foil here, what is going to happen is it's going to start cooling this bulb. All right, it's going to start cooling this bulb, and the amount of water vapor that is coming off this bulb and going into the atmosphere is going to be inversely proportionate to the amount of water vapor already present in the atmosphere. So if there's less water vapor in the atmosphere, it's going to aggressively pull more amount of water vapor from this bulb, which is going to cause its temperature to reduce further. All right. So even though that you are measuring the dry bulb temperature, you also need the wet bulb temperature to accurately measure or to get a reference point to measure the humidity within the air mixture. Is that clear? So we have got two reference points. One is the dry bulb temperature and one is the wet bulb temperature.